I want you to just take a moment and look at the screen you're reading this on right now. Or if you happen to be near one, just glance over at a window. Just kind of look at the glass for a second.
Yeah, we usually don't give it a second thought, do we?
No, not at all. And, usually when we talk about the physical world, there's this deep expectation of precision. Like, if you look at a solid piece of steel, you know beyond a shadow of a doubt that it's a solid.
Right, absolutely.
And if you look at a glass of water, you know it's a liquid. It's binary. It's comforting, honestly. We rely on that fundamental predictability to just sort of get through our everyday lives.
We really do. I mean, our entire intuitive understanding of the physical universe is built on these neat, easily categorized states of matter. We like to know the rules of the game.
But then you step into the world of glass, and suddenly that neat binary system just shatters. The rules don't apply. We're looking at this everyday material, something you probably touch, hundreds of times a day?
Oh, easily hundreds of times.
And it is actually the absolute definition of diagnostic muddy waters in physics. It just completely defies standard categorization.
It's a profound, silent mystery, sitting right there in plain sight. At an atomic level, it's a non-equilibrium state, trapped in this highly viscous pause. It's really a material caught between identities.
And that is exactly what we are exploring today. Welcome to Decoding the Dark. Today, we're intentionally slowing things down. We are going to take a relaxing, contemplative journey into one of the most beautiful and honestly confounding mysteries of the physical world.
It's a perfect topic to just sit back and absorb.
It really is. And before we dive into the deep end, please take a moment to subscribe and like this channel, Decoding the Dark. Your support is what allows us to keep bringing you these soothing explorations of the universe's most hidden secrets.
It is wonderful to have you with us for this journey today, because today's topic, while it seems ordinary, has genuinely baffled some of the greatest minds in physics for nearly a century.
We have an incredibly diverse stack of sources for this deep dive. I'm looking at historical timelines of ancient Mesopotamian civilizations, exhaustive encyclopedic reviews from material scientists, cutting-edge quantum physics simulations from just the last few years, and even the latest medical research on bioactive materials.
Yeah, the breadth of the research is really necessary here because glass doesn't belong to just one field. To even begin to understand it, you have to synthesize geology, theoretical thermodynamics, chemistry, and, as you mentioned, modern medicine.
Our mission for this deep dive is to answer what seems like, on the very surface, to be a ridiculously simple question. What exactly is glass? We're going to journey from the violent volcanic dawn of human civilization to the mind-bending quantum theories of broken bonds.
We're also going to finally debunk a centuries-old urban legend that you've probably heard a dozen times on tours.
Oh, definitely. And ultimately, we'll reveal how this bizarre phase of matter might soon be used to seamlessly heal your broken bones or, allow us to injection mold jet fighters. So let's just settle in, take a deep breath, and start at the very beginning. Because long before human beings were melting sand to blow vases, the Earth was forging glass in intense natural fires.
Right. If we want to understand what glass fundamentally is, looking at nature's manufacturing process is the perfect starting point. And nature's method is violent, rapid, and incredibly effective.
The most famous natural glass that comes to mind, and our historical sources talk about this extensively, is obsidian. We see it used in ancient arrowheads and cutting tools. So obsidian forms when lava erupts from a volcano and cools rapidly. But what exactly is happening during that rapid cooling that makes it glass, rather than just, a normal rock?
It all comes down to kinetic energy and molecular mobility.
Yeah.
When magma is deep inside the Earth, it's incredibly hot, and its constituent atoms, which are primarily silicon and oxygen, are moving around freely in this chaotic liquid state.
Okay, so they're just sloshing around.
Exactly. Normally, as magma cools slowly deep underground, those atoms lose kinetic energy very gradually. They have enough time to find each other, form specific chemical bonds, and arrange themselves into neat, repeating three-dimensional geometric patterns.
Like a grid.
Right, that orderly arrangement is what we call a crystal lattice.
Yeah.
And that's how you get things like granite or quartz.
So they have time to organize the dance floor before the music starts.
That is a fantastic way to visualize it. But with obsidian, the lava is ejected onto the Earth's surface, or, right into the ocean, where the temperature drop is just catastrophic and sudden.
It's a massive shock.
A huge shock. The lava cools so incredibly fast that the atoms are stripped of their kinetic energy before they have any time to organize. The viscosity of the liquid skyrockets instantly. The atoms literally freeze in place, trapped in that chaotic, jumbled, liquid-like arrangement. they're locked into what we call an amorphous solid.
And because it freezes so chaotically, without the natural grain boundaries or cleavage planes that you'd find in a crystal lattice, it yields a material of astonishing sharpness. The sources highlight that obsidian glass edges can reach almost molecular thinness.
It's true.
Like, a freshly fractured piece of obsidian is sharper than a surgical steel scalpel, which is a wild to think about.
It is wild. The structural disorder allows it to fracture along a continuously smooth curve, which geologists call conchoidal fracture, right down to the width of just a few atoms.
Yeah.
But beyond its sharpness, what's truly staggering is its chemical stability.
Yeah, I was reading the geological records in our stack, and they mentioned that some natural glasses can survive in highly erosive, harsh environments for up to 300 million years.
Millions of years, yeah.
They have an alteration rate of less than a single millimeter per million years. How does a disordered, chaotic mess of atoms achieve that kind of near immortality?
Well, nature acts as an unparalleled master chemist here. The sources provide the exact chemical composition of a typical California obsidian, for example. It's roughly 75% silicon dioxide, which forms the primary chaotic network.
Okay, 75%.
But it also contains about 13.5% aluminum oxide, along with smaller, tightly controlled amounts of iron oxide, calcium oxide, sodium oxide, and potassium oxide.
So it's a very specific recipe. It's not just random dirt.
It is highly specific. The aluminum, in particular, tightly bonds with the silicon and oxygen network. Even though the overall structure lacks that long-range order, the localized chemical bonds between these specific elements are incredibly strong.
Oh, I see.
They form a dense, impenetrable amorphous web that water and corrosive chemicals simply cannot easily permeate or break down. It's really a masterpiece of geological chemistry.
And volcanoes aren't the only extreme environments creating this stuff. We also have tektites and moldavites. These are born from something even more violent than a volcano.
Right, the sheer kinetic energy of a large meteorite striking the Earth. When a meteor hits, the impact generates localized temperatures and pressures that are almost incomprehensible to us. It instantaneously melts the Earth's surface rock.
Just vaporizes and melts it.
Exactly. This molten material is violently ejected high into the atmosphere, and as it travels through the much colder air, it cools rapidly, freezing into small, glassy objects before it even hits the ground again. The moldavites found in Central Europe, which have this beautiful translucent green hue, are estimated to be about 15 million years old, born from an impact in what is now southern Germany.
Okay, so let's unpack this for a second. Nature has been producing perfect glass for hundreds of millions of years via meteors and volcanoes. But the human timeline presented in our historical sources is fascinatingly delayed. Human glassmaking didn't start until around 3500 BCE in Mesopotamia and Egypt.
That's right.
And initially, they weren't making windows, they were just making tiny, opaque, decorative beads.
Yeah, the technological leap from finding glass to manufacturing it is massive. It requires mastering intense heat and complex chemistry.
Well, I want to push back on that human timeline a bit, though.
Yeah.
If you're an ancient human, you have sand everywhere, you have fire. Why did it take until 3500 BCE to figure this out? And more importantly, how did they stumble upon the exact recipe? Because the sources are very clear, making glass isn't just taking a handful of sand and throwing it into a campfire.
No, it's definitely not. And this raises an important question about ancient ingenuity. To understand why it was so difficult, we have to look at the chemistry of the ingredients. The factual recipe for a glass batch requires three highly specific interdependent components. First, you need a former.
Former.
Right, this is the foundational building block of the glass structure, which is almost always silicon dioxide derived from high-quality quartz sand.
And silica is incredibly tough stuff.
Incredibly tough. The covalent bonds between the silicon and oxygen atoms are so strong that pure silica has a melting point of over 3,000 degrees Fahrenheit, or roughly 1,700 degrees Celsius.
Wow.
Ancient kilns, fueled by wood or charcoal, simply could not generate that kind of sustained, localized heat. The technology to melt pure sand just didn't exist yet.
So the ancient Mesopotamians hit a thermal wall. They needed a chemical shortcut to get around the limitations of their furnaces.
And that shortcut was the second ingredient, the flux. Ancient glassmakers discovered that if they added certain alkaline substances to the sand, specifically soda ash derived from burning coastal plants or potash from wood ashes, something magical happened. The flux significantly lowers the melting point of the silica mixture.
But how does ash lower the melting point of sand? What is actually happening in the fire?
Well, when you heat the soda ash, it breaks down and releases sodium ions into the silica. Remember those incredibly strong silicon-oxygen bonds we just talked about?
Yeah, the ones that need 3,000 degrees to break.
Right. The sodium ions act like microscopic wedges. They actively break the continuous three-dimensional network of silica bonds, creating what chemists call non-bridging oxygens. Because the network is chopped up into smaller, less connected chains, it requires drastically less thermal energy to turn the whole mass into a liquid.
That makes total sense.
With a flux, they could melt the batch at around 1500 to 1800 degrees Fahrenheit, which was well within the capabilities of ancient kilns.
So they solved the heat problem by chemically chopping up the sand. That's brilliant, but our sources point out a massive flaw in this two-part recipe. If you just mix silica and a flux like soda ash, the result is practically useless.
It is. The resulting material is called water glass. Because the flux has severed so many of the strong silica bonds and replaced them with highly reactive sodium ions, the resulting glass is actually water-soluble.
Wait, water-soluble?
Yeah, if you shaped it into a cup and poured water into it, the glass would slowly dissolve into a sticky alkaline puddle.
That is not going to work for an empire trying to build vessels for wine and olive oil.
Not at all. So they needed a third crucial ingredient to rescue the structural integrity of the material: the stabilizer. The ancient glassmakers turned to limestone, or crushed seashells, which provided calcium oxide.
And what is the calcium doing to fix the water problem?
At an atomic level, the calcium ions are divalent, meaning they can form two bonds. They step into the molecular gaps created by the flux and essentially act as microscopic bridges, cross-linking the fragmented silica chains back together just enough to restore chemical durability.
Oh, that's clever.
The stabilizer prevents the glass from dissolving in water, it stops it from cracking as it cools, and it inhibits unwanted crystallization. You carefully proportion the former, the flux, and the stabilizer together to form the batch, you heat it in a kiln, and you get true, stable, molten glass.
It's mind-blowing to consider the trial and error required for ancient civilizations to land on that perfect chemical trifecta. I mean, they didn't have periodic tables, they couldn't see molecules, they just kept adjusting the ash, the shells, and the sand over generations.
It's a testament to human persistence.
And this chemical mastery eventually triggered what the historical texts call the first golden age of glass during the Roman period, roughly from the 1st to the 4th century CE. That is when glass transitioned from being a rare luxury item owned only by pharaohs to a genuine household necessity.
The Romans were unparalleled engineers. Once they adopted the blowpipe, which was a Syrian invention from the 1st century BCE, they industrialized glassmaking. They understood its physical properties intimately. They knew how it stretched, how it cooled, how it held its shape, even if they lacked the terminology of molecular physics to explain why it behaved that way.
And it is precisely those physical properties, how glass seems to stretch and flow, that leads us perfectly into one of the most enduring, stubborn scientific myths of our modern era. It's a myth that perfectly illustrates how confusing this material really is to our intuition. We need to talk about the cathedral myth.
Ah, the famous flowing windows. It is perhaps the most widely circulated misunderstanding in all of materials science.
If you're listening to this and you've ever taken a tour of a majestic medieval cathedral in Europe, or honestly, if you've even just sat through a high school chemistry class in the last 50 years, you've likely heard this story. The tour guide points up at these gorgeous, soaring, stained glass windows and confidently says, notice how the glass panes are thicker at the bottom than they are at the top. That's because glass isn't a true solid, it's a supercooled liquid. Over the centuries, gravity has slowly, imperceptibly pulled the liquid glass downward, causing it to pool at the base of the lead frames.
It's a great story.
It sounds so incredibly poetic. It has this veneer of deep scientific truth to it.
It does. It has a certain intuitive logic that makes it an incredibly sticky urban legend. We know glass requires heat to mold. We know it can slump in a kiln, so the idea that it might slowly slump over centuries at room temperature it feels plausible. But we must emphatically debunk this myth using the definitive evidence from our sources. At room temperature, glasses are amorphous solids. They do not flow on any human, historical, or even geological timescale.
Okay, but let's play devil's advocate here for a second. If it's a complete myth that they flow, why are the cathedral windows demonstrably thicker at the bottom? The tour guides aren't making up the physical shape of the glass. The bottom heaviness is an observable fact.
Right, the thickness is real. But the variation is entirely an artifact of the manufacturing process used by medieval glaziers, a technique known as the crown glass process. To understand the windows, you really have to understand how they were made.
Okay, how do they do it?
A medieval glass blower would take a glowing lump of molten glass from the furnace on the end of a hollow pipe. They would blow it into a large hollow globe. Then, They would transfer that globe to a solid iron rod called a punty, puncture the globe to open it up, and reheat it. Once it was soft, they would spin the punty iron as fast as they could.
Oh, this is exactly like a chef spinning pizza dough in the air. When you toss and spin dough, the centrifugal force pushes the mass of the dough outward, away from the center. The middle gets stretched incredibly thin, and a thick, heavy crust accumulates around the outer edge.
That analogy perfectly captures the physics of the process. The centrifugal force in the crown glass method caused the hollow globe to rapidly flare out and flatten to a large, flat disc, sometimes several feet across. But just like the pizza dough, the outer edges of that glass disc were naturally much thicker than the center where it was attached to the punty rod. It also had these concentric ripples radiating outward.
So you have this giant, uneven disc of glass. Then what?
When the glass cooled, the glaziers would score it and cut it into small rectangular panes to fit into the lead cane of the cathedral windows. Because they were cutting these rectangles out of a disc with a thick outer rim and a thin center, almost every pane they cut had a thick end and a thin end.
And if you're a medieval glazier, standing on scaffolding trying to build a stable window that can withstand wind and weather, what are you going to do? You're obviously going to install the pane with the heavy, thick side at the bottom to lower its center of gravity within the lead frame. You wouldn't balance a heavy rock on top of a thin stick. It was a structural engineering choice, completely devoid of centuries of slow dripping.
A purely practical structural choice. And we have undeniable empirical evidence to prove that flow is impossible. The sources point specifically to the lifetime work of Robert Brill. He was an incredibly prominent researcher at the Corning Museum of Glass, who dedicated over 30 years to studying antique glass.
What did he find?
Brill meticulously analyzed the composition, the stress patterns, and the physical profiles of ancient glass. He definitively confirmed that the ripples, the striations, and the thickness variations are simply manufacturing artifacts. They bear the undeniable mechanical hallmarks of spinning and rolling, not gravitational flow.
The sources list some incredibly old pieces of glass to back this up, too. We have the Augsburg Cathedral windows in Germany, which date back to the 11th century. We have the breathtaking North Rose window in Notre Dame from the 13th century. And going back much further, we have the Roman Portland vase, which is an incredibly delicate cameo glass vessel from the 1st century AD. If glass flowed, a delicate carved vase from 2,000 years ago would look like a melted candle by now. But its intricate details remain razor sharp.
And if we connect this concept to the broader realm of precision optics, the argument against flow becomes absolute. Consider astronomical telescope lenses manufactured 150 years ago. Optical glass requires uncompromising nanometer-level perfection to focus light properly. If the glass in an observatory lens had flowed even a fraction of a micrometer over a century and a half due to gravity, the focal point would shift.
The images would be ruined.
The airy discs would distort, the lenses would be completely ruined for scientific observation, but they remain optically flawless today.
So the flowing window myth is completely, totally busted. Glass is not a liquid slowly sliding down a cathedral wall. But here's where it gets really interesting. The reason this myth survives so stubbornly in the public consciousness is because it's rooted in a very real, very complex physics problem. Physicists themselves have struggled for decades with how to define the transition between a liquid and a glass.
The confusion is entirely understandable when you look at the thermodynamic data. Glass exists in a bizarre physical limbo. Structurally, it lacks the long-range crystalline order, the regular, repeating geometric lattice of a true solid like ice or metal. If you look at it under an electron microscope, the atoms are arranged haphazardly, just like they are in a liquid.
Yet it clearly possesses the mechanical rigidity of a solid.
Right.
Let's really break down that transition, because this is where our everyday intuition just fails us. Normally, state changes in matter are pretty straightforward. If you take a glass of liquid water and put it in a freezer, the temperature drops until it hits exactly 32 degrees Fahrenheit, or 0 degrees Celsius. At that exact moment, it undergoes what physicists call a first-order phase transition.
During a first-order phase transition, a few highly specific things happen simultaneously. First, there's a release of latent heat. Even though the surrounding environment is cold, the water molecules release energy as they bond. Second, there is a dramatic discontinuous change in volume and heat capacity. And third, the chaotic water molecules suddenly snap into a highly rigid, orderly, hexagonal crystal structure.
Boom!
Boom! Liquid water transforms into solid ice at a discrete, easily identifiable thermodynamic point.
But glass refuses to behave like that. When you cool a batch of molten glass-forming liquid, it doesn't have a sharp freezing point. There is no sudden release of latent heat. There is no snapping into a crystal lattice. Instead, we have to look at something called the glass transition temperature, denoted in the literature as TG.
And exactly what happens at TG is the heart of the mystery. As the liquid drops below its melting point into a supercooled state, it doesn't crystallize. Instead, its viscosity, its resistance to flow, begins to increase exponentially. It gets thicker and thicker, more and more sluggish over a broad range of temperatures. Eventually, as it cools past TG, the molecules lose so much thermal energy that they become kinetically frozen in place.
I always picture it like a snapshot of a crowded, chaotic dance floor. The exact second the music stops, everyone is frozen in whatever awkward, random position they happen to be in. There's no orderly grid, no lines, just suspended, static chaos.
That captures the structural reality perfectly. And the sheer scale of the viscosity change during this cooling process is almost impossible to wrap your head around. The sources note that the viscosity of a typical glass-forming liquid rises by over 17 orders of magnitude within a relatively narrow temperature window of about 500 Kelvin.
Let's just pause on that number for a second for the listener. 17 orders of magnitude. That is a 1 followed by 17 zeros. It goes from flowing somewhat like honey to possessing a resistance to flow that is astronomically high, effectively acting like a rigid stone.
Yeah, and because of this continuous creeping change in viscosity, rather than a sudden phase snap, defining exactly when the liquid becomes a glass used to be somewhat arbitrary. For decades, scientists essentially drew a line in the sand. They agreed on a convention that said, if a supercooled liquid reaches a viscosity greater than 10 to the 12th Pascal seconds, or 10 to the 13th poise, we will officially categorize it as a glass.
But picking an arbitrary number like 10 to the 12th Pascal seconds sounds more like an administrative convenience than a fundamental law of physics. It's like saying a person officially becomes old the millisecond they turn 65. It doesn't reflect the underlying biology, or in this case, the underlying physics.
Precisely. And the sources highlight the fundamental flaws in relying on that arbitrary definition. Take the organic compound phenyl salicylate, commonly known as Salol. Researchers meticulously measured Salol as it cooled into a glass. The thermodynamic data shows that the viscosity of Salol, precisely at its calorimetric glass transition temperature, its TG, is more than 2 orders of magnitude below that standard 10 to the 12th Pascal second mark.
Oh, wow.
So defining the glass state purely by a universally applied viscosity threshold completely falls apart when you look across different materials.
If the classic viscosity threshold is broken and there is no crystal lattice to identify, how do modern physicists actually define what glass is?
To resolve this, researchers Edgar Dutra-Zanotto and John C. Mauro published a comprehensive review proposing a highly precise dual definition. For the general public, they simplified it to this. Glass is a non-equilibrium, non-crystalline state of matter that appears solid on a short time scale, but continuously relaxes toward the liquid state.
Okay, wait, hold on. Continuously relaxes toward the liquid state. Are you saying the glass in my window right now is actively trying to become a liquid?
Yes. It is in a non-equilibrium state, meaning it possesses excess thermodynamic energy that it sort of wants to shed. It is microscopically, imperceptibly shifting, relaxing, in an attempt to reach a stable state. Zanotto and Mauro's more rigorous academic definition goes further. They state, glass is a non-equilibrium, non-crystalline condensed state of matter that exhibits a glass transition. The structure of glasses is similar to that of their parent supercooled liquids, and they spontaneously relax toward the supercooled liquid state.
So what does this all mean for the glass sitting in my house? If time and temperature are somewhat interchangeable in the physics of glasses, and they are constantly in this agitated non-equilibrium state, trying to relax, what is their ultimate destiny? If we wait long enough, say billions or trillions of years, what actually happens to that glass?
It is a profound, almost philosophical concept in thermodynamics. In the absolute limit of infinite time, the ultimate thermodynamic fate of glass is to solidify completely, to crystallize.
Really?
Yes. The atoms within the glass are currently trapped in a high-energy disordered state. They are stuck in local energy minimums, unable to overcome the kinetic barriers to rearrange themselves. But over incomprehensibly long timescales, thermal fluctuations will eventually allow those atoms to shuffle themselves into the lowest possible energy state, which is a highly ordered, perfect crystal lattice.
So if I somehow leave a drinking glass on my kitchen table for longer than the current age of the universe, it won't melt into a puddle of liquid. It will eventually rearrange itself into an opaque, crystalline rock.
Yes, its final inevitable fate is to become a true crystalline solid.
That is absolutely mind-bending. But this bizarre limbo state, this concept of a frozen liquid that is thermodynamically desperate to become a crystal, led to one of the most massive physics paradoxes of the 20th century. It haunted scientists for 75 years and sent the entire field of materials science down a theoretical rabbit hole. Let's delve into the Cosman paradox.
This paradox is a classic, beautiful example of how taking a mathematical model and extrapolating it to its absolute logical extreme can completely break our understanding of physics. It was ignited in 1948 by a brilliant chemist named Walter Cosman.
Cosman was studying these supercooled liquids we've been talking about, and he noticed something deeply troubling about their entropy. For our listeners, let's establish a baseline entropy is essentially a measure of the disorder, the randomness, or the number of microscopic configurations available to a system.
Right.
A liquid has very high entropy because its molecules are sloshing around chaotically. There are millions of ways to arrange them. A crystal, on the other hand, has very low entropy because every atom is locked tightly into a neat, perfect, highly predictable grid.
That is a perfect summary. So Cosman was painstakingly tracking the entropy of a liquid as it was supercooled below its melting point. Naturally, thermodynamics dictates that as the liquid gets colder, the kinetic energy of the molecules drops, they slow down, and the configurational entropy decreases. The liquid becomes incrementally more orderly as it prepares to freeze.
But Cosman did what inquisitive scientists do. He looked at the curve on the graph and he extrapolated the data. He drew the line further down into temperatures that hadn't been experimentally reached.
He extrapolated the cooling trend of the liquid's entropy past the glass transition temperature, plunging it down toward absolute zero. And when he followed the math, he found a theoretical temperature point, which we now refer to as the Cosman temperature, or TK, where the entropy curve of the supercooled liquid would violently cross the entropy curve of a crystal.
Oh, wow.
Yeah, this meant the supercooled liquid would theoretically possess less entropy than a perfectly ordered crystal for the same temperature.
I have to stop you there because based on the laws of thermodynamics we just established, that sounds physically impossible. You're saying the mathematical models predicted that a messy, jumbled, amorphous liquid could possess less disorder, more absolute perfection than a flawless, geometrically rigid crystal? How does the math even allow for that?
The math allowed for it because of the equations they were using to model the viscosity and relaxation times of the liquid. Specifically, many physicists relied on empirical models like the Vogel-Filter-Tammand equation or the VFT equation. The VFT equation is widely used to describe how the viscosity of a glass-forming liquid shoots up as temperature drops.
Okay.
But the VFT equation has a mathematical quirk. It features a singularity. It predicts that at a certain finite temperature, often very close to the Cosman temperature, the viscosity becomes infinite and the relaxation time becomes infinite. If you plug that infinite viscosity into the thermodynamic models for entropy, the entropy curve plunges straight down, crossing the crystal line.
That is the paradox. It blatantly violates the third law of thermodynamics, which implies that as a system approaches absolute zero, its entropy approaches a constant minimum. A chaotic, disordered liquid cannot, by definition, have lower configurational entropy than a perfectly ordered crystal lattice. It is a fundamental contradiction in terms. The scientific community dubbed it the entropy crisis.
It was a massive crisis. You had a fundamental thermodynamic law on one side and the accepted mathematical models of supercooled liquids on the other, and they were careening toward a collision.
How did Cosman himself explain his own paradox? Did he just throw his hands up and say the math was broken?
No. His proposed solution was incredibly pragmatic. He argued that the liquid is essentially forced to crystallize before it ever has a chance to reach the Cosman temperature. He theorized that as the liquid cools and approaches this impossible thermodynamic state, the energy barrier required for crystallization simply vanishes. The liquid realizes it's about to break the laws of physics, so it spontaneously and rapidly snaps into a crystal to avoid the entropy crisis altogether.
The universe protecting its own rules. But that wasn't the only solution proposed by the scientific community. Other theoretical physicists looked at Cosman's data and said, what if the math isn't broken and it isn't forced to crystallize? What if this curve is pointing to a completely undiscovered, radically new phase of matter? The sources refer to this hypothetical state as ideal glass.
The concept of ideal glass is mesmerizing. Theorists hypothesized a state where the amorphous molecules are packed together as densely as physically possible, resulting in zero configurational entropy, but they still remain entirely random in their arrangement. There's no repeating lattice. It would be a true, distinct thermodynamic phase of matter, structurally unstructured like a liquid, but possessing the ultimate density and hardness of a diamond.
But ideal glass sounds like an oxymoron. Ordered randomness, perfectly dense chaos. Why couldn't they just take a super cooled liquid, stick it in a highly controlled cryogenic lab, cool it down to the Cosman temperature, and prove whether ideal glass actually exists or if it crystallizes?
Because of the crushing tyranny of the timeline required. To allow the molecules to pack that densely without accidentally jostling into a crystal formation, you would have to cool the liquid at an excruciatingly slow rate. As the temperature drops, the viscosity rises astronomically, meaning molecular movement takes longer and longer.
How long are we talking?
By the time you get near the Cosman temperature, the time it takes for the molecules to find that perfect, random packing arrangement would exceed the current age of the universe. The material becomes so incredibly viscous that the molecules just grind to a halt in a standard glass state long before they ever reach the ideal state. It is experimentally inaccessible.
So we can't make it in physical reality because we don't have billions of years to spare. But we can cheat. We have immense computational power. The sources mention Eric Corwin, a physicist at the University of Oregon, who decided to use supercomputers to bypass the physical time limits of reality.
Yes, Corwin and his team designed brilliant algorithms to simulate a two-dimensional version of this ideal glass transition. They essentially programmed a simulation where they swapped particles mathematically to force them into tighter and tighter packing arrangements, bypassing the kinetic slowing down that happens in reality. They forced the simulated particles to achieve maximum density without crystallizing.
And what did the simulation show? Did it work?
It did. They created a digital state known as hyperuniformity. The simulated structure was completely random on a local scale, no repeating patterns, yet it was perfectly mathematically even in density across the entire simulation, with absolutely no voids or microscopic clumps. It proved that the structural concept of ideal glass is mathematically and geometrically possible.
Okay, so a supercomputer says ideal glass can exist as a geometric concept, but what about the Cosman paradox itself and the messy real world of thermodynamics? Did we ever actually solve the entropy crisis that started this whole 75-year debate?
According to a recent incredibly exhaustive review published by Zanotto and Mauro, who we mentioned earlier, the Cosman paradox has officially been retired. After 75 years of intense debate and the publication of over 400 scientific papers dedicated to solving it, they concluded that the entire crisis was essentially a phantom.
A phantom? You mean the math was just wrong the whole time?
Yes. The crisis was manufactured by flawed mathematical extrapolations. Remember the Vogel-Fulcher-Taman equation we discussed, with its singularity that drives viscosity to infinity at a finite temperature?
Right.
Zanotto and Mauro argue that while the VFT equation is great for modeling viscosity at higher temperatures, it completely breaks down and fails at the extreme low temperatures of deep supercooling. Modern advanced thermodynamic models, combined with vast amounts of new simulation data, show that the entropy of a supercooled liquid doesn't plunge into a singularity. Instead, the curve flattens out. The entropy decreases smoothly, gradually, and asymptotically towards 0 Kelvin, without ever crossing the crystal entropy line.
Oh, I see.
Therefore, there is no impossible drop in entropy. There is no forced crystallization necessary to save the universe, and there is no entropy crisis.
So it was essentially a mathematical divide by zero error embedded in an old equation that sent generations of brilliant scientists on a 75-year wild goose chase.
In many ways, yes, it was a wild goose chase, but it was an incredibly fruitful one. To prove the paradox wrong, the scientific community was forced to develop entirely new, vastly more accurate mathematical models for understanding deep supercooling, relaxation times, and the fundamental nature of amorphous materials. The journey advanced the field immensely.
Okay, so if the Cosman paradox is officially retired, and we don't need a magical, thermodynamically impossible ideal glass phase transition to save the laws of physics, how do modern physicists actually explain the exact mechanical moment a flowing liquid becomes a rigid glass? Because if the atoms are structurally disordered in both the liquid state and the glass state, what actually changes mechanically at TG?
To finally understand that mechanism, we have to undergo a paradigm shift. We have to stop looking at the chaotic atoms themselves and start looking at the empty space between them. This brings us to a breakthrough theoretical framework called configuron percolation theory, or CPT.
Configuron percolation theory. That sounds incredibly intimidating, like something out of a quantum field theory textbook. Let's break that down for the listener.
It sounds complex, but it's actually a very elegant, intuitive way to understand the glass transition. Instead of focusing on the tangled, chaotic positions of the atoms, CPT focuses on the connectivity of the system. Specifically, it looks at the state of the chemical bonds between the molecules.
Okay, so atoms are connected by chemical bonds. We established that with the silica network earlier.
Right, and CPT introduces a pseudo-particle concept called a configuron. Configuron isn't a physical particle like an electron. It is a localized structural excitation. In simpler terms, a configuron is a broken chemical bond within the material's network.
Just a broken bond. Got it. So how does focusing on broken bonds explain why a glass window is hard, but molten glass flows?
It is entirely about the topological arrangement of these broken bonds. Let's look at the material below the glass transition temperature when it's a hard, solid glass. Even in solid glass, there is thermal energy causing vibrations, so some bonds will occasionally break. But these broken bonds, these configurons, exist only as isolated, lonely point defects scattered throughout the vast, intact network of the glass. In mathematical terms, the theory states that their Hausdorff-Bisikovich dimension is strictly zero.
Okay, you just lost me there. A dimension of zero, like a dot on a piece of paper. It has no length, no width, no height. It's just a mathematical point.
Exactly. Because the broken bonds are isolated points, they cannot communicate or interact with each other. The overwhelming majority of the chemical bonds in the network are perfectly intact. Therefore, the macroscopic structural integrity of the atomic network is uncompromised. The glass acts like a rigid, inflexible solid, but as you heat the glass up in a furnace, you add massive amounts of thermal energy. That energy violently vibrates the atoms, causing more and more bonds to snap. You generate more and more configurons.
And what happens mechanically when you finally hit that magic glass transition temperature, TG?
A profound topological phase shift occurs. Suddenly, the density of broken bonds reaches a critical threshold. There are so many configurons that they are no longer isolated. They begin to touch and connect with each other. At TG, the fractal dimension of these connected broken bonds instantly jumps from 0 to 2.55.
I need to challenge that number, a dimension of 2.55. How does something exist in half a dimension? It's either a 2D flat plane or a 3D cube. What is 2.55?
That is the beauty of fractal geometry. The Hausdorff-Bisikovich dimension measures how a complex, irregular shape fills space. Think of a perfectly flat piece of paper that has a dimension of 2. Now think of a solid ball of clay that has a dimension of 3.
Right.
If you take that piece of paper and tightly crumple it up into a ball, it is no longer truly 2D, but it doesn't completely fill the 3D space like the solid clay. It is a fractal. Its dimension lies somewhere between 2 and 3. The broken bonds in the glass at TG form a fractal structure with a dimension of roughly 2.55. They form a macroscopic percolating network.
A percolating network, so instead of isolated dots of broken bonds, they link up into a massive, tangled, three-dimensional web that permeates the entire material.
Exactly. It becomes a continuous interconnected web of nothingness, a web of broken bonds that spans from one side of the material to the other. And this interconnected web fundamentally compromises the rigid network. It creates pathways that allow the atoms and molecules to slip and slide past each other. The material loses its rigidity and begins to flow like a highly viscous liquid.
So, if I'm understanding this clearly, if you are listening to this and holding a glass of water, the solid glass in your hand isn't rigid because the atoms are frozen in place. Melting glass isn't about giving the atoms themselves enough energy to move at first. It's about creating a continuous highway of broken bonds that the atoms can then slide through.
That is a brilliant visualization. The atoms are structurally disordered in both the solid glass and the flowing liquid states. The critical phase change happens entirely within the bonds. This cooperative dynamic, the way the broken bonds suddenly link up to form a highway or suddenly collapse back into isolated points, is precisely why the viscosity skyrockets so dramatically as the material cools. Once the highway of broken bonds severs and collapses into isolated dots at TG, the atoms have nowhere to slide. They're trapped. The material is kinetically frozen.
That is profoundly beautiful. We are essentially looking at the architecture of nothingness, the macroscopic connectivity of broken things, dictating how the physical world behaves. And what's wild is that this isn't just theoretical chalkboard physics anymore. This deep atomic level understanding of how the glass transition works, how the network of bonds behaves, is allowing scientists to do some incredible, almost science fiction level engineering in the real world.
Yes, moving from the theoretical realm of Cosman and configurons to applied engineering. we're witnessing a genuine revolution in material science. Because once you understand the mechanics of how to control the chaotic structure of a supercooled liquid, you don't have to limit yourself to traditional silica sand. You can apply the glass transition to entirely different classes of materials.
Like metal. Let's talk about bulk metallic glasses, or BMGs. When I think of metal, when I think of steel girders or aluminum airplane wings, I think of a highly organized crystalline structure. The atoms are perfectly lined up in a grid, which is what gives metal its legendary strength.
Traditionally, yes, all the metals we use in engineering are crystalline. But material scientists realize that the configuron percolation theory applies universally.
Mm.
If you take molten metal and you can figure out a way to cool it down unbelievably fast, that we were talking about quenching it at rates of millions of degrees per second, you can outrun the crystallization process. You can trap the metal atoms in a chaotic amorphous structure just like silica glass. These are bulk metallic glasses.
But why would we want metal to act like glass? Glass shatters when you drop it.
To answer that, we have to look at the weak points of regular metals. Crystalline metals aren't just one giant perfect crystal. They are made up of millions of microscopic crystal grains pressed together. The borders where these different grains meet are called grain boundaries. In material science, grain boundaries are inherent structural defects. They are the exact places where the metal is most likely to corrode, where stress fractures initiate, and where structural failure begins. Bulk metallic glasses, because they are amorphous, have absolutely no grain boundaries. They possess a perfectly uniform, chaotic atomic structure across the entire material.
And what does a metal without grain boundaries act like?
It acts like a supermaterial. It becomes incredibly strong, often 2 to 3 times stronger than titanium alloys. It becomes phenomenally scratch resistant, highly resistant to corrosion, and surprisingly elastic. It can absorb impact energy and bounce back in ways that crystalline metals simply cannot.
But the sources say there is a massive historical trade-off that scientists are currently battling to solve with BMGs. They aren't perfect yet.
Right. There is a severe thermodynamic trade-off between stability and ductility. To make a metallic glass thermodynamically stable, so it doesn't accidentally heat up and spontaneously snap into a brittle crystal, you have to design the alloy so its atoms pack together extremely tightly into a low-energy state. But packing them that tightly eliminates any free volume for the atoms to move under stress. This makes the material extremely rigid, but catastrophically brittle. If you hit it hard enough, it won't bend. It will shatter like a glass window.
So it's incredibly strong right up until the exact moment it explodes into shrapnel.
Precisely. On the other hand, if you tweak the alloy to make the metallic glass ductile, meaning it has some microscopic free volume allowing it to bend and deform plastically without breaking, it becomes thermodynamically unstable. The atoms have too much room to move, and over time, or under slight heat, they will find their way into a crystal lattice, ruining the glass properties.
So we have this theoretical supermaterial, but we are walking a tightrope trying to control it.
We are getting closer, though. Remember Eric Corwin's computer simulation of ideal glass? By using advanced computational models to perfectly map the glass transition and predict how different atomic sizes pack together, scientists are designing novel, multi-element metallic glass alloys. They are trying to find the Goldilocks stone, a metallic glass that retains its chaotic, grain-free structure, but possesses enough localized ductility to prevent shattering.
The sources mention that if we can fully solve this ductility problem, the manufacturing implications are insane. We could literally injection mold jet fighters or complex car engines. You just pour molten metallic glass into a highly intricate mold, it cools into an amorphous solid, and you pop out an entire engine block with 0 grain boundaries, 0 weak points, and no need for machining or welding.
It would completely revolutionize aerospace and automotive engineering.
Yeah.
Though while bulk metallic glasses are still heavily navigating the research and development phase, there is another application of advanced glass science that is already changing lives right now, and it is happening deep inside the human body.
This might be the most counterintuitive and surprising part of our entire deep dive: bioactive glass. We usually think of glass as something intensely dangerous to the human body. If you step on a shard of broken window glass, you are going to the emergency room to get stitches. But bioactive glass represents a total paradigm shift in modern medicine.
It is a remarkable, profound innovation. Conventional window glass, like the silica we discussed earlier, is biologically inert. If you put it in the body ignores it. Bioactive glass, however, is specifically chemically engineered at the atomic level to interact dynamically with living biology. It possesses the unique, seemingly magical ability to chemically bond with living tissues, both hard bone and soft tissue.
The sources trace this medical revolution back to the late 1960s to a brilliant material scientist named L.L. Hench, who invented a specific glass composition called 45S5.
Yes, Larry Hench created a specialized silicate-based glass. Unlike steel window glass that uses a lot of silica and calcium to prevent dissolving, Hench intentionally designed 45S5 with a lower amount of silica, about 45%, and a very specific high ratio of calcium and phosphorus along with sodium. This deliberate composition makes the glass highly reactive. When 45S5 is surgically implanted and exposed to physiological fluids, like human blood plasma or interstitial fluid, it immediately undergoes a complex cascade of chemical reactions.
Walk us through that cascade. How does a piece of glass talk to a human bone?
First, the sodium and calcium ions within the glass rapidly exchange with hydrogen ions in the body's fluids. This creates a localized alkaline environment and leaves behind a porous silica gel layer on the surface of the glass. Next, calcium and phosphate ions from both the glass and the surrounding body fluids migrate into this silica gel layer. They precipitate out and form an amorphous calcium phosphate layer. Finally, within hours, this amorphous layer crystallizes into hydroxycarbonate apatite, or HCA.
And why is HCA so important?
Because HCA is biologically and chemically identical to the mineral phase of natural human bone. By forming this HCA layer, the glass effectively camouflages itself. It literally signals the body's native bone-building cells, the osteoblasts, to migrate to the area, attach to the HCA layer, start replicating, and lay down new, living bone matrix directly onto and into the glass surface.
That is incredible. The glass tricks the body into thinking it's already bone, triggering a massive healing response. But how is this actually applied in surgery? The medical sources in our stack talk extensively about using bioactive glass to coat metallic orthopedic implants. Why do we need to coat them? If a patient needs a total hip replacement, the surgeons usually use solid titanium, right?
Titanium, and specifically its alloys like Ti6Al4V, are the absolute gold standard for load-bearing joint replacements because they possess the incredible mechanical strength required to support human body weight. But titanium implants have a major fundamental flaw. They are not bioactive. When you hammer a titanium stem into a femur, the body recognizes the metal as a massive foreign object.
So the patient's immune system attacks the new hip.
It doesn't reject it like a mismatched organ, but it tries to isolate it. The body's natural defense mechanism is to form a layer of dense, fibrous scar tissue, completely enveloping the titanium implant, trying to wall it off from the rest of the body. This is called fibrous encapsulation. Because of this scar tissue barrier, the living bone can never truly mechanically bond to the metal surface. It just rests against it. Over years of walking and stress, the implant can become loose within the bone canal, leading to severe pain, micromotion, and eventual catastrophic failure of the joint replacement.
Not to mention the issue of long-term corrosion. The sources point out that the physiological fluids inside the human body are essentially warm, highly oxygenated salt water. It is a highly corrosive environment. Over decades, even titanium can begin to corrode and wear, releasing microscopic toxic metal ions and wear debris into the surrounding tissue and the patient's bloodstream.
Which can trigger severe localized inflammation, metal hypersensitivity, bone death osteolysis, and severe long-term health complications. So, the orthopedic field faced a massive dilemma. They desperately needed a way to bridge the gap between materials. They needed the massive mechanical load-bearing strength of a titanium core, combined with the biological friendliness and bonding capability of natural bone.
Enter the bioactive glass coating.
Precisely. By coating the titanium implant shaft with a microscopic layer of bioactive glass, you completely alter the interface. When the surgeon inserts the implant, the body doesn't see a foreign piece of titanium. It interacts solely with the highly reactive glass surface. The glass immediately begins forming that HCA layer we discussed. The body reads it as bone. The fibrous scar tissue encapsulation never forms. Instead, the patient's natural bone grows directly into the glass layer, creating a profound, unbreakable biomechanical bond that locks the titanium implant permanently into the skeleton.
Okay, I have to play the skeptic again. We are talking about putting glass inside the human body, specifically on a hip or knee joint that takes the full impact of walking and jumping. If I jump off a step, isn't the brittle glass coating on my hip implant going to shatter under my weight?
It's a very logical concern based on our everyday experience with windows. But the engineering at play here is spectacular. These coatings are not thick layers like a window pane. They are engineered to be incredibly thin, often measured in just a few dozen micrometers. At that microscopic scale, the mechanical properties of the underlying massive titanium rod completely dominate the structural behavior. The coating simply flexes with the metal. Furthermore, the bioactive glass coating is specifically designed to be resorbable.
It dissolves away.
Yes, dynamically. As the natural bone grows, remodels, and integrates deeply with the HEA layer, the bioactive glass network slowly dissolves. It releases its calcium and silica ions, which are safely metabolized and excreted by the body. Eventually, months after surgery, the glass coating is entirely gone. You are left with healthy, natural bone bonded directly and intimately to the microscopic topography of the titanium, with absolutely no glass remaining in the body.
That is absolute genius. But mechanically getting that pristine layer of glass to stick onto the titanium in a factory sounds like a complete nightmare. The engineering sources list a dizzying array of coating techniques: thermal plasma spraying, high-velocity suspension, flame spraying, sol gel methods, electrophoretic deposition, laser cladding. It sounds like the industry is throwing every physics concept at the wall to see what sticks.
They are, because permanently fusing glass to metal is an immense thermodynamic and engineering challenge. Let's look at the most common industrial method, which is thermal plasma spraying. In this technique, you inject finely milled bioactive glass powder into a plasma flame that is thousands of degrees hot. The glass particles melt instantaneously into liquid droplets and are shot at supersonic speeds onto the roughened titanium substrate, where they splatter, flatten out, and rapidly cool to form a continuous coating. But wait, there's a massive thermodynamic trap there, isn't there? We just spent the first half of this deep dive talking about how heat, cooling rates, and the Kosman paradox affect the atomic structure of glass. Exactly, you've hit the nail on the head. If you blast the bioactive glass powder with a plasma flame, you risk heating it too much, altering its delicate chemistry. More importantly, when those molten droplets hit the titanium, they must cool rapidly enough to freeze back into an amorphous glass state. If the coating cools too slowly, the atoms will do what all glass ultimately wants to do. They will find their lowest energy state and crystallize.
And why is crystallization bad in this context? We said crystals were stable.
But stability is the enemy of bioactivity. If the bioactive glass crystallizes, it locks all those crucial calcium and sodium ions tightly into a rigid geometric lattice. The material loses its chaotic amorphous structure and drastically loses its ability to react with the body fluids. It won't form the HCA layer, and it won't bond to the living bone nearly as well.
So the engineers are walking an incredibly tight tightrope. You have to literally blast the glass with a superheated plasma flame to melt it onto the metal, but you have to instantly freeze it fast enough on the surface so it doesn't organize into a useless crystal.
And if that wasn't hard enough, you also have to perfectly manage the coefficient of thermal expansion. When the hot titanium and the hot glass cool down together after spraying, they shrink. But metal and glass shrink at different rates. If those expansion coefficients don't match perfectly, the immense stress will cause the glass coating to develop microscopic cracks and flake off the implant before it even gets shipped to the hospital.
So how are material scientists actually solving these massive manufacturing hurdles?
By returning to the foundational chemistry of the glass batch. Instead of relying solely on the original 45S5 recipe, scientists are doping the glass network. They are strategically introducing specific trace elements into the silica matrix to fundamentally alter both its thermal manufacturing properties and its biological healing properties.
What kind of elements are we talking about?
For instance, they add trace amounts of magnesium or strontium oxides to the patch. These specific elements disrupt the crystallization process. They raise the crystallization temperature of the glass, widening the thermal processing window. This makes it much easier to plasma spray the powder without it accidentally turning into a rigid crystal. But brilliantly, this doping serves a dual purpose. When the glass dissolves in the body, it releases those strontium ions. Clinical research shows that strontium actively interacts with the bone cells, enhancing the replication of osteoblasts while simultaneously suppressing osteoclasts, the cells that break down bone. It literally supercharges the biological bone healing process.
It's an incredible two-for-one solution. Better, more reliable manufacturing in the factory, and significantly faster, stronger healing for the patient. The sources also mentioned doping the glass with elements like silver, copper, or zinc.
Yes, those specific elements are introduced not for bone growth, but for their potent, localized antibacterial properties.
Yeah.
In orthopedic surgery, implant-associated infections are catastrophic. They're incredibly difficult to treat because bacteria form biofilms on the metal, and the infection often requires a massive revision surgery to physically remove the prosthesis. By incorporating silver or copper ions directly into the atomic matrix of the bioactive glass, the coating slowly and steadily releases a localized, highly concentrated antibacterial defense right at the surgical site. It actively poisons and prevents bacteria from colonizing the implant during those critical first few weeks while the bone is healing and vulnerable.
It is truly staggering how far we have journeyed today. We started this deep dive looking at ancient Mesopotamian bead makers, standing around rudimentary kilns, blindly mixing sand and plant ash, desperately trying to mimic the sharp, volcanic obsidian forged by the earth.
We traveled through the medieval era, looking at the breathtaking stained glass of Notre Dame, taking the time to thoroughly debunk the persistent myth of the flowing windows and proving the rigid, amorphous reality of the material.
We plunged into the absolute mind-bending depths of thermodynamics. We explored the mathematical contradictions of Walter Kaufmann's entropy crisis, the theoretical computer simulations of perfectly dense ideal glass, and the elegant fractal mathematics of configuron percolation theory, where a sudden macroscopic web of broken bonds dictates whether a material is solid or liquid.
And we finally emerged at the absolute cutting edge of modern bioengineering, where we are actively designing 3D printed, ion-releasing bioglass to trick our own immune systems into healing our skeletons.
It is a journey that I hope truly changes the way you look at the physical world around you. I mean, look around wherever you are sitting right now. Look at the glass screen of your smartphone, or the windows in your living room, or the glass you drink water from. We intuitively think of them as permanent, static, boring objects. But they aren't. They are in a highly agitated, non-equilibrium state. They are trapped in a highly viscous kinetic pause, silently and microscopically relaxing.
They are, quite literally, a chaotic liquid desperately trying to organize itself, frozen in time.
And I want to leave you with one final, incredibly provocative thought to ponder. Something to mull over the next time you gaze out a window. Because we established that the ultimate thermodynamic fate of all glass is to eventually shed its excess energy, seek its lowest energy state, and crystallize. Which means every single piece of glass you see in your life is technically dying. It is on an incredibly slow, inexorable journey toward order. If you wait long enough, perhaps far longer than the current age of the universe, every window pane, every astronomical telescope lens, every fiber optic cable, and every smartphone screen on Earth will eventually surrender its chaotic, transparent beauty. It will inevitably arrange its atoms and turn into a perfect, rigid, opaque crystal.
It is a profoundly beautiful and perhaps slightly melancholic scientific truth. In the grand timeline of the universe, thermodynamic order always wins in the end.
It always does. Thank you so much for joining us on this deep, contemplative journey today. We hope you found the exploration of this diagnostic, muddy water as relaxing, informative, and mind-bending as we did. Please, if you enjoyed this deep dive, take a moment to subscribe and like Decoding the Dark. We want to keep exploring the beautiful, quiet mysteries of the universe with you. Until next time, remember to keep looking closer at the everyday things you think you completely understand. Stay curious.